All right, let's take a look at another example. Before I do that, I want to fix something here. I just realized that I did not find the square root of 21. So if you do that, you'll actually get 4.58 meter per second, which means I have to fix this one as well. This is gonna be 4.58 ER. Right, that makes more sense now. All right, just a quick fix there. Forgot about the square root. Now let's look at this example. Right, this is again a disk, a table, circular table. You have a block this time, block M. You can think about it, block B actually. I guess that's why it would be there. So block B put on the table. This table is rotating with the angular velocity of 20 radian per second. And let's see what the problem statement is telling us and what we are supposed to do with this situation. So the problem statement is telling us that the circular table, the circular table is being driven at a constant angular velocity just theta dot is equal to 20 radian per second about the vertical z axis. Right? We're told that the block B, right, of mass m is equal to well, let's just keep it that way. Mass m is placed on the rotating table we'll just leave it there. So with 0 initial velocity. All right. Let's also add this part to it with the velocity with this the string AB taut. That's it, taut. Now, here's what we're told. We're told that if the block slips, if block right slips for 3.11 for 3.11 seconds, right? Before it reaches the speed of the table, rotating table, for 3.11 seconds before reaching the speed of the table, we're told to find the coefficient of kinetic friction between the block and the table. All right, so it's a little bit of different type of problem or problem statements, the same story, but you're just trying to change the wording and look at the problem from a different angle, or give you at least a different perspective from what you might see in typical type of problems in this under this topic. All right, so here is what's going on. This table is rotating with 20 radian per second. We know the angular velocity. Now, this block B is attached to this vertical axis Z using this string, while this string is totally stretched. Right? We put the block on the disk, this rotating table. Right? Just leave it there. So with initial velocity, we put it there. What happens is that at the beginning, it starts slipping. Right? This table is rotating with 20 radian per second, so it's going fast. So at the beginning, the block is sliding, and it takes about 3.11 seconds before the friction between this rotating table and the block can actually hold the block on the table and overcome or stop any slipping, and at that point the block is rotating at with the same velocity as this table. Right? So that's a general idea, and we know the length of this spring is 0.5 meters. Right? Hopefully you get what's going on here. Now we are given some information. We are given the velocity of this disk, right? 20 radian per second. We know it takes 3.11 seconds before this block before this block has the same velocity as the rotating table. The initial velocity of the block is 0. We just leave it there, and we are asked to find the coefficient of kinetic friction. Right? That's what we are trying to find. Now, look at what we are given. Well, we have the angular velocity. We know the initial velocity, right? Initial velocity of the block, and initial velocity also of the table, rotating table. We know the time interval. So these are the things we know, and you can see that this is a rotating motion. So you can get a sense of this is a central force motion. How is that a central force motion? You might ask. If I draw the free body diagram for this block, let's see if I can do that. Let's see what we have there. We have its table. So this is the weight. Let me put it here. This is the weight downward, mg. There is a normal force between the table and the block, right? So that's N. We do have the tension because of this string, right? It's going in this direction, obviously. So I'm going to put it here. This is the tension. You can see that right there, T. Let me erase that one. And remember, there is a friction between this block and this rotating table. Now, pay attention to which direction you should put the friction. Friction is always in the opposite direction of the motion of the object. Right? So when we put the block there, just think about what happens. This table is rotating in this way. At the beginning, the block starts slipping. Right? So while this is going this way, the relative motion between the this rotating table and the block would be in this direction. Right? This is rotating, block cannot catch up with this rotating table, so it falls behind. This is slipping. Since it's slipping in this direction, right? The slipping can't go with the same speed as the table at the beginning. So since that would be the motion in this direction, the friction would be in opposite direction. So that would be your friction. So I'll put the friction here. All right, if we look at it this way, I can put the friction in this angle. This would be Fk. Mu k, yeah, it's a slip. Right. Hopefully that makes sense. Again, table is rotating, the block is slipping, it's sliding. It takes some time to catch up with this table. So the block is moving in this direction. The relative motion between the block and this rotating table is, since the table is going counterclockwise, the relative motion between the block and the table would be clockwise. As a result, the friction is in the opposite direction. Friction is always in the opposite direction of the motion. All right. Now, let's see what we have. We have velocity, we have time, and we want to look at force because we're trying to find the coefficient of kinetic friction. So we have to look at the friction. So we have to take into account the force. So force, time, velocity. Let's go back. Principle of linear impulse and momentum gives us force, time, velocity. That's one possible way of looking at it. The better way would be using principle of angular impulse and momentum, right? Because we have a central force motion. Well, actually, we don't have a central force motion. I have to correct myself because we said the resultant force should be. I'm glad I draw the free body diagram. So it could be a very common mistake, which I even got into the same trap. We say the resultant force should be toward a fixed point in our coordinate frame. Now, resultant force is not in that direction. T is in that direction, but now we have friction, right? So the resultant force between these two is not toward a fixed point. That's actually changing because the friction is changing. Right. So if I didn't have friction and it was just T, it would have been a central force motion. But in this case, I have T towards a fixed point, but Fk or friction is not. Right. So this force during this motion is actually not toward, or it does not remain toward a fixed point with respect to a reference frame. I hope I fix that there, and you actually now, or maybe you realized that from the beginning and you were just yelling at me saying, no, it's not the central force motion. Yes, you're right, if that was what you were saying. It's not the central force motion. So we have the relationship. If that would have been if it was the case, then we couldn't really take the force into account. Right? So we have time, we have velocity, and we want to take into account the force, and we have this distance r. Right? The distance, one thing that stays constant is this distance r, right? Where the block is with respect to the z-axis. So we are going to use principle of angular impulse and momentum, the full expression, the complete expression. Right? And that was the expression, and that's why I brought this example here. So you see one case in which we do not have a central force motion and we have to actually use the whole equation. So the whole equation was from R1 to R2, not R1, R2, T1 to T2. Right? This is momentum. T1 to T2, R cross F dt is equal to HO2 minus HO1. Again, the reason I'm using this, velocity, time, I know the position. And I have to take into account the force because I'm trying to find the coefficient of kinetic friction, which means I have to actually have my friction force in this expression somehow. All right, see what we get here. we have, let's go one by one. Let's start with this part. R is, let me see if I can draw. Okay, so this integral, let's say from, let's call this 1. For this, we calculate this integral separately here. From 0 to t, from the moment I leave it there till sometime t. Or what is R? R is, let's look at this polar coordinate system. I'm going to draw it here. ER, maybe I can do it a little better than that. ER E theta, right? ER E theta. So this is, your R would be RER, RER, just the vector R in ER direction. Cross, let's see what we have as a force. Now, remember your force is, well, let's write it this way. It's minus T ER, right, plus mu K N E theta. Right? It's a cross product, so I have to actually write the whole vector with its components. Now, if you do this cross, well, obviously here you have also dt. If you do this cross product, this one to this one, and then this one cross this one. See what we get. RER cross minus TER, ER cross ER. Two vectors parallel, or in this case, they are the same, right? ER and ER. So the sign between, the angle between these two is 0, right? Remember, A cross B is AB sine theta. Sine 0 is 0, so that becomes 0. Nothing comes out of this. This is 0. The second one, RER cross mu K and E theta. Remember the ER, E theta, EZ for cross product. Right? ER cross E theta becomes EZ, EZ cross ER becomes E theta cross EZ becomes ER. If you go in the opposite direction, E theta cross ER becomes minus EZ, EZ cross E theta becomes minus ER, E theta cross ER becomes minus EZ. Okay, say that. So if you go in the opposite direction, it becomes negative. So this one becomes R mu K N ER cross E theta becomes EZ. And let's also put T there. If you take the integral from 0 to T dt, nothing is function of T, so that becomes T E theta. Now from free body diagram, you know N is equal to mg. So I'll put it here. R mu K mg E theta, right? So that's the left side of this equation. Let's look at the right side, this side. From the right side, I'll get HO2 minus HO1. Now, HO, remember what HO was. HO was R cross MV. V, the vector, or position vector, V velocity vector. You have to be very careful with these equations. You have to go term by term and make sure you take into account all details and directions and vectors. Right? Be patient with these. You rush it, you're going to make mistakes. All right. So I forgot about T here. There you go. My mistake. So HO2 minus HO1. All right, let's see what we get from there. HO2, let me see if I can write it this way. HO2 would be R2 cross M V2, and HO1 would be R1 cross M V1. Right. Looking at the first one, R1 is well, R ER cross, well, what is V1? Initial velocity is 0. So this is actually 0. So this whole thing becomes 0. Let's look at the second position. R2 is R ER cross M. V2 will be M VR in R theta coordinate system, right? So this becomes R theta dot let me write it properly, E theta. E theta. Right? You're in let me just write here. You are in R theta coordinate system. If you look at this, let me draw it here, see if it, this is ER, this is the top view, this is VR, this is V theta. Remember, VR was R dot ER, V theta is R theta dot E theta. Now there is no R dot, R is fixed, right? You don't really have any change in R. That's why this becomes 0. That's why I didn't put it here. V theta is R theta dot E theta. And I put it right here. Right, it's a component of velocity at point 2. So continuing this, again, cross product. ER cross E theta. Follow the circle. ER cross E theta becomes EZ. So that becomes M R squared theta dot EZ, which I just realized that I should have put EZ here too. So there you go. EZ and EZ. ER E theta becomes EZ. So now we have the left side, and this comes out of the left side, this comes out of the right side. Just make them equal. Let me do that. The left side was M, was mu K mgr T is equal to, both of them are in Z direction, so I'll just ignore the Z unit vector, or you can just put it here just for the sake of completeness if it makes you feel better. EZ, right, that would be EZ is equal to mr squared, remember, theta dot EZ. Right, both of them are in Z direction, which it should be, otherwise we would have had a problem here. M and M can be canceled from both sides. Right, and from there you will get mu K is equal to R squared theta dot over G R T. You can also cancel 1R from both sides. You will get R theta dot over GT. R is 0.5 times theta dot is 20 meter per second. G equals G. And time is 3.11 seconds. All right. So that should give you mu K, which will be 0.328. All right. So this was an example of how to implement the complete equation for, we should be probably a little more careful and use vector sign here. So, you know, these are all vectors, even if I don't put them there. How to use the complete expression for principal angular moment, principle of angular moment, let me go there, angular impulse and momentum. All right, we used the complete equation. It was not a central force motion. We had friction there, so there was the resultant force was not. It was not in the same direction. It did not remain, or it was not remaining toward the fixed point during the motion. A fixed point in a reference frame. It was not remaining toward a fixed point in a reference frame during the motion. So it was not a central force motion. So we had to write the whole expression. And we were looking at the relationship between force, time, position, and velocity. So that's how we ended up using principle of angular impulse and momentum. Right. Just one thing that you really have to be careful, as I said before, is that you have to be careful about these cross products and make sure that you do it correctly, write everything in vector form. As I said, when we talk about momentum methods, directions matter. We have to represent variables, position, velocity, momentum, force. We should represent all of them in vector form. So it becomes very important to make sure that we get the directions right, we get the representations in our coordinate system right, and do the cross product correctly. So there's so many details there that, frankly, there are so many details that can go wrong. So you have to be very careful when you're implementing this method. And also always look at the problem to get a sense of when to use which one. Principle of linear impulse and momentum, principle of angular impulse and momentum, or energy methods. Right? The problems usually can be involved more than one of these methods. Easily it can be extended to some point that you have to use two methods simultaneously or one after another to be able to solve the problem. All right.